Hello, my name is Clemens. I'm the CTO of Percival, and today we're going to talk about timing effects in simulation. In my last video, I showed you our sensor model development library, the SMDL, and how to use it to build up sensor models that are based on standardized interfaces. And today I'm going to go a little bit more into detail of different effects you can simulate using the SMDL. And the topic of today is timing effects. I will start with going back to the example I showed you in the last video. If you recall, it was this one. This highway scenario with a car driving on it, and we have this 360-degree scanning lidar on top of this vehicle. And I don't know if you noticed in the last video, but if you look closely to some of the points in the point cloud, you will notice some effects. For example, look at this one here. We have this pole here on the side of the road. You notice there are no points on that pole. Let me actually move a little bit closer here. And you can see there are no points on this here, but there are points here. So you might wonder, what's this? Is this an error in the simulation, or where is it coming from? Actually, no. This is called the motion scan effect. So for a scanning lidar like this, you have it on top here, and it spins. So it's a rotating lidar. And of course, while it is spinning, the car moves further. Not only the ego vehicle, also all the other cars and everything that's moving in the scene moves further. So we don't have still images. This is very similar to motion blur in cameras. And by the time the lidar has spun through the point where it's shooting its beams towards this pole here, the cars move further. And that's why you have a distance between the actual pole here, which is visualizing the first time step of that scene, and the actual points in the point cloud. So the SMDL uses that, and the SMDL uses velocity information of all moving objects to move them further in the scene for that particular simulation time step. So that's the first effect you have when it comes to timing. For a second effect, I'm going to open up another trace file here with another sensor. Let's open up this one. So we're loading the scene again. And this sensor here is a prism lidar. And this prism lidar has a non-repeating beam pattern. So the beam pattern is actually different in every simulation time step. And that's also something that you can simulate with the SMDL. Using the SMDL, you have the freedom and the possibility to define a new beam pattern for every single time step. So the beam pattern can change. And you see here you have these curves here at the edge of the beam pattern. And if I play this back now, you will notice that they change. I can also do this step by step, and you'll notice that these lines and their orientation change over time. And that's something that's very easy to simulate with the SMDL. You just calculate a new beam pattern based on the data you have of your sensor, and it's just one function call, update beam pattern. And you have a new beam pattern for every new simulation time step. And of course, these two effects can also be combined. And I will open up another trace file for that. This is an example of a MEMS lidar. So a lidar that has oscillating mirrors. And in this case, the beam pattern also changes. It alternates between every other frame. And this also affects timing, because in a MEMS lidar, you only have a couple of lasers that through the oscillation of the mirror build up the whole beam pattern. So you also have a change in the beam pattern throughout one scan. Let me actually move forward. We have this gantry here, and that's where you can very easily see that effect. I move a little bit to the side here. So take a couple of steps closer to the gantry. And you see here the same effect we had on the poles. Just in this case, it's not a spinning lidar, so it's not a horizontal effect, but the beam pattern is built up vertically. That's why you see here it starts at the bottom, where you have the points here. We actually make the points a little bit bigger. By the way, you see the analysis capabilities of SimSpectre, right? You can analyze your sensor data right in there in the 3D environment. You can alter how big the points should be, and you can set this perfectly to how you can analyze your point cloud, your simulated point cloud, just as a side note. And you see here, it starts at the bottom. So at the bottom, your points are very close to the actual gantry pole here. And then they go out at the top because the car moves toward the gantry while the beam pattern is built up with the mirrors of the MEMS lidar. So you can see that here. And you also see it on the other side. Now if I go one step further, you see it changes because it alternates. It builds up the beam pattern from the bottom to the top in one frame, and then in the next frame, it goes from the top to the bottom. That's what you can see here. So now it's closer at the top and going further away at the bottom, and it alternates between frames, and you can neatly see that here. Then beam pattern actually is a little bit complex, more complex than that. So you have multiple lines multiple paths of the actual beams that overlap. So it gets a bit more complicated here the closer you get to the gantry. So you see here two effects combined, changing the beam pattern from one frame to the other and having the so-called motion scan effect. So having everything that's moving the scene move further during one frame of the simulation. And that's all something that the SMDL takes care of. So don't have to worry about the mechanics of it and the simulation of it. As long as your input data is there and you calculate the different beam patterns for different frames and you set a timing offset for every beam, the SMDL takes care of the rest. I will put a link in the description to the sensor model development library and also to SimSpectre, so you can check out further details on our website. Thanks for watching, and I'll see you in the next video.